Good morning, boys and girls, and welcome back to another day of the chain rule. Yesterday we kind of got into it a little bit and started to really look at our inside versus outside functions, what that u should be. So when I take the derivative of something, I take it with respect to u and then times u prime. Today we're going to kind of get into it some more, and we're going to go a bit deeper today and get a little crazier. So to start our discussion today, we're going to look at these four functions I have up on the the screen here. We really got to pay attention to where parentheses are now, because depending where they're at with things like cosine and sine, our trig functions, or even like ln's or e's, or we're going to really handle them differently when we take their derivative. So if I'm looking at the blue one here first, if I'm looking at cosine of 3x squared, this has no parentheses, but it's implied that the 3x squared is in the argument of cosine. So like I really could put parentheses there, but a lot of times you won't see that. If I were going to take the derivative of this, I definitely have an inside function and an outside function here. So I can start by taking the derivative of the outside function. Derivative of cosine is negative sine, and the inside function stays the same. And then chain rule says, hey, now I'm going to take the derivative of the inside function. So times 6x. So this derivative would be negative sine. Nope, not that. That's not what I wanted. Negative 6x sine 3x squared. Okay, so that's how I do that one there. Versus if I had cosine of 3 in parentheses now and the x squared outside, well, now that cosine of 3 is really just a number. So that just becomes a coefficient. It's a crazy coefficient, but it's just a coefficient. So if I were to take the derivative of this, now I would just use the power rule and multiply the 2 times in front. So 2 cosine of 3 x, and that goes down by 1. And so that would be its derivative. For the green one here, cosine of 3x squared. Okay, again, this really all becomes inside the argument of cosine. So like before, we take the derivative of the outside function, negative sine of 3x squared. But now I've got to take the derivative of that inside. And when I look inside now, I've got a function inside another function. Oh my God. I'm going to have to do chain rule again. 2 chains. I don't know if you remember, I have the record in my room of 2 chains, the wrapper. This is why. Okay? 2 chains. I'm going to have to do the chain rule twice. So now I have to multiply this by derivative of the u, inner u now becomes 3x, right? So this is 2 times 3x to the first. And then I can take the derivative again of the inside times 3. And we're going to do that a little bit slower here in a second, but I mean, that's how crazy. We can have chain upon chain, functions stacked inside of functions, and so we really got to watch out and pay attention. All right? If I clean this up now, we would get something like 3 times 2 is 6 times 3 is 18. So negative 18x sine of 3x squared. Okay? Would be the derivative of that. And then our last one now, cosine squared of x. Okay? If I've got cosine squared of x, this one we just got to watch out. When that little squared's there, we got to know that this really, it doesn't look like it has an inside function, but it does, because this is cosine of x squared. So really I have an inside and an outside function, and that's just kind of what we just got to know the difference with. If I had to take the derivative of this, derivative of the outside function, 2 cosine of x to the first times the derivative of the inside, negative sine x. So negative 2 sine x cosine x. Or maybe again on this one, they would write this as negative sine 2x using our little our identity. Okay. So these are 4 things that look kind of similar, but the way we took the derivative is very, very different for each of these. So we kind of got to be careful and really pay attention to what your inside and outside function is. Okay, before we get too much further here, because we're going to be dealing more with these trig functions, I quickly want to review the derivatives of our trig functions. We said, hey, make sure you know the 3 on the left, the 3 in black. The derivative of sine is cosine, derivative of tangent is secant squared x, and the derivative of secant is secant x tangent x. Okay? Because if you know those, the ones on the right then again are the negative co-functions. So the derivative of cosine is negative sine x, because that is the co-function for cosine. The derivative of cotangent is negative cosecant squared x. since cotangent is the cofunction of tangent, and cosecant is the cofunction of secant. Okay? And then the derivative of cosecant x is negative cosecant x cotangent x. Okay? Know these 6 derivatives. You just have to have them down and memorized. Hopefully you have that taken care of by now. Okay, so here we go. And we want to take the derivative of sine 2x squared. All right? So we had that discussion to begin this set of notes here. And we said if we saw sine of 2x squared, that implies that this is inside the argument, or that is on the inside of the parentheses. And in the beginning, if it helps you to rewrite it like that so you see an inside, totally go and do that. Okay? This, again, would be my u. You know, my u would be 2x squared. And if it helps you to write that out in the beginning, go ahead and do that. All right? So if I can take the derivative of sine of 2x squared, well, the derivative of sine is cosine. And then again, this part stays the same, right? The inside stays the same. Cosine of u times u prime. So now I need to multiply this by the derivative of u. And the derivative of 2x squared is, or the derivative of the inside is, 4x. And so now, this one wasn't too bad, reorder things, and we get 4x cosine of 2x squared. And that would be our derivative. Okay? That's a problem kind of like yesterday's stuff where we just had, you know, one chain rule that we had to apply. Here's where we're going to move on more towards today. Okay, now I want to take the derivative of sine of 2x squared. And again, it might help you if you use, you know, really practice, emphasize using your inclusion symbols. Again, when I have sine of 2x, we said that's really inside the argument. I'm going to use like maybe some brackets here now since I already have parentheses. And so you can see, like, because I've got the 2 sets of parentheses, I've really got 2 sets of inside functions. Okay? My first one being, you know, u is sine of 2x, right? And then my second inside function I'm going to have to deal with is, I'm going to call it double u. Get it? Double u, because it's the... Okay, never mind. But that's 2x. I crack myself up. All right. So now when I go to take the derivative of this function, again, I got to start with the outside function. So the outside would be this u squared if I rewrote it, right? So the derivative of u squared would be 2u, or u again is sine 2x to the first power, right? Then I need to multiply this by u prime. So I'm going to come over here and find u prime. U prime is derivative of the outside function here now is cosine of 2x. And then because I had that inside function, that w here technically, right? I now need to multiply this by w prime, or 2. So this whole, putting this all together, and I know I'm kind of scattered here a little bit, putting this all together, the derivative of the outside, 2 sine 2x to the first, times the derivative of the inside, cosine of 2x, times the derivative of the inside, times 2. That's generally what our work's going to look like right there. Okay? And if it helps to break it up and actually write in some u's and w's so you can kind of see what's happening, that's not a bad thing. You know, maybe you wrote this as, you know, u squared times u prime, and then when you came here, you had, you know, you had to say that u is sine of w, and then, you know, to take u prime, you're going to multiply it by, you know, this times w prime. You know, if you have to write it out like that a little bit to help kind of organize your work in the beginning, that's fine. We're going to get to where eventually, though, and hopefully we're not too far off right now, eventually, though, we can just go ahead and write it like that. Technically, I've now taken the derivative. Maybe all I need to do is just kind of clean this up a little bit. So again, this would be 4 sine 2x cosine 2x. And again, whenever you get this sine 2x, cosine 2x, sine x, cosine x, like on the first one, I'm thinking this is a double angle. I'm not going to see this answer like that in the back of the book. I'm going to guess this is going to be 2 times 2 sine 2x cosine 2x. And this, again, is my double angle. So this becomes 2 sine 4x. And I'm betting that's our answer for the derivative. Let me go and check. And yep, that's exactly what they had. Alright, couple more now. Let's get a little crazier still. Okay, so here's where things start to get just a little bit crazier. I want to take the derivative of this function. My advice to you is going to be to rewrite this so that you see with your inclusion symbol, so you see all the different inside functions. Okay, so I've got two sets of parentheses or inclusion symbols, so I know I'm going to have to do chain rule more than once. I shouldn't have put the prime in there yet because I just rewrote it. That's still just y. All right, so if I do take the derivative of this y prime, okay, I get 1/2 first at the outside function, right? 1/2 times 3x minus 4 squared plus 3x. That all stays the same. All to the negative 1/2 because I subtract 1 just using power rule. Then I need to multiply chain rule. I need to multiply this by the derivative of the inside. So I'm going to start taking the derivative of the inside here, and again, term by term. So if I take the derivative of this term, I would get times 2 times 3x minus 4 to the first. And then again, because this had an inside, I've got to chain rule again. 2 chains times 3. Now I'm done taking the derivative of this term, so I can take the derivative of the next term, plus 3. And again, using different inclusion symbols I think really helps, and it helped me when I first started doing this. Now I've technically taken the derivative, and now I need to go ahead and just simplify what's going on here. 1/2 3x minus 4 squared plus 3x to the negative 1/2 times, if I simplify this here, I'm going to get 6 times 3x minus 4 plus 3. Okay. Or if I multiply all this stuff on top here, 6 times 3 is 18x. 6 times 4 is minus 24, plus 3 is minus 21. This 1/2, the 2 would go on the bottom, right? The 1 on top. And because this had a negative exponent, this would go on the bottom 1/2 as a radical. And there's my derivative the way it looks in the back of the book. You can take it up here, we had it, even this very first red step, but we need to go ahead and simplify all the way and make it match the back of the book, and that's how I did it in this problem here. Alright, one more problem. Okay, last problem here. This one we're going to have some fun. Okay, y equals tangent of x e to the x. We obviously have a chain rule involved here, right? Because we have an inside, but inside of our chain, we're going to use, product rule, it looks like. Okay, our rules, they do mingle. They're not one-off rules. Okay, so we got to be able to use multiple rules at the same time. So if I go ahead and start tackling this thing here, y prime is the derivative of tangent is secant squared x e to the x, derivative of the outside, so secant u, secant squared u, times the derivative of the inside. When I do the derivative of the inside, now I've got a product, so I have to use product rule. So derivative of the first times the second plus the first times the derivative of the second. Or now I just need to clean things up a bit. Secant squared of x e to the x times e to the x plus x e to the x. Or I think what we would do with this thing here now is I can factor out an e to the x from this here. So I think I'd factor that out to the front. That would leave me with 1 plus x, or x plus 1. And then we'd be left with our secant squared x e to the x. And that is the answer in the back of the book, boys and girls. Okay? So you can see, I don't know, maybe you need to watch these more than once or twice. But do please pay attention. I'm hoping I'm not making it look way easier than it seems.
For your information, there's a lot more to ogres than people think. Example? Example? Okay, ogres are like onions.
They stink?
Yes. No.
Oh, they make you cry?
No.
Oh, you leave them out in the sun, they get all brown, start sprouting little white hairs.
No. Layers. Onions have layers. Ogres have layers. Onions have layers. You get it. We both have layers.
Oh, you both have layers. Oh. Not everybody like onions.
So just remember, boys and girls, derivatives have layers too. Watch out for him.